So here, this is the problem statement that is given as let, so this set P is given. So x belongs to this interval that is 0 to 4 pi, and it is strictly given that tan x squared is not equal to 1. And here set S is given as A, and A belongs to the set of integers. And this A is constrained by this particular equation here. And here x belongs to P. So in this equation, whatever this appearance of x is there, x must take up the values from this particular set P, right? So in that case, we need to write this set as in roster form, and we need to compute the number of elements present in set S. So first of all, whatever is given, I'll proceed with the given data sets. So given is this P that is clearly visible, right? So instead of writing it, I can just directly use it from here. So this P is already given and the set S is given, right? So I'll proceed with this equation first of all, that is given in set S. Now I'll take this and write it here for once, and in the next step I can write this one as, so what I can do, I can write a square here, a square is equal to this, and I can just eliminate this part. So it is same writing, right? Or maybe I can just write it over here, that is a square is equal to this, fine. So just the representational aspect. Now proceeding ahead, so this implies, now this cos x power 8, right? So here I'll take the power 4, and outside this I'll be writing 2, and the same thing I'm going to do it for sine as well. So sine of x power 4, and this will be squared, right? And for now I'll keep this secant of 2x as it is, because I'm not able to observe any cancellations or any kind of expansion here. So let's focus on this part first of all, right? So let us go step by step. Wherever I'll be feeling that secant of 2x must be resolved, so in that case we'll think about it. Now here this is in the form of a square minus b square, so that is nothing but a plus b minus, sorry, a plus b times a minus b. So here a plus b times a minus b, right? So that is cos x power 4. Now if you observe this part, that is this cos x power 4 minus sin x power 4. So here again we can decompose this part, right? So I'll take this and decompose this part. So I'll be writing it at first, and then I'll be decomposing it in the next step. Now here this one, if you observe, I can just write this one as cos x squared and again squared on top of it. Similarly for this one, sin x squared and here squared on top of this, right? So now in the next step, again I'm going to apply the formula, that is identity a square minus b square. So from this one we can write, that is cos x square plus sin x square times the very same quantity with negative sign. So this one with the negative sign, and we can clearly observe that this one is 1, right? So in the next step I'll take this one and replace it with 1. So this is the identity that we already know, correct? And this cos square x minus sin x squared, this can be written as cosine of 2x. So this can be written as cosine of 2x. So finally we have this expression. So let me repeat again. So this becomes 1, and for this expression we are writing cosine of 2x. So now if you observe this cos 2x and secant of 2x, so this will, I'll be using the reciprocal identity here, and this will resolve to 1. So again I can just eliminate this part as well. So finally this is my equation that I am having over here, right? Now we are aware of this fact. So how are we so sure that if this secant of 2x is replaced as 1 by cosine of 2x, so how we are sure this at this point that this cosine of 2x is not 0? So for this it is already mentioned, so I'll definitely mention the reason. It's already given that tan x squared is not equal to 1. So this clearly implies that cosine of 2x cannot be, this cannot be 0. So because of this guarantee, I am able to cancel out this thing, if in case this is the doubt, right? Now I'll proceed with this given equation. So here I'll be applying the identity. So first of all, I'll just transform this little, that is cos x squared whole squared, and this one sin x squared, and then again on top of this I'll square this one. Now here I'll be applying the identity of a square plus b square. So in this part, I'll be writing here this one as cos x squared. So this will be cos x squared plus sin x squared, and here minus 2 times sin x squared, and then here I'll be writing cos x squared. Now this expression, if you observe this sub expression, this again for this one we can use the identity, right? So that resolves to 1. So this part resolves to 1. Now here if you observe this 2 times cos x square and sin x squared, so this can be written as 2 times sine of 2x squared. So instead of this one I can write 2 times sine of 2x squared, sine of 2x squared. Now this is the equation that we are having finally. Now we know this fact again. So since it is squared function, that is sine 2x squared, so I'll be talking around the range of this one. So what I'll do in the very next step, so we are aware of this, okay? Instead of this I will focus on this particular quantity. So if you observe this value, so I can just talk about the range of this one, that definitely this will be greater than or equal to 0 because it is squared, and this will be less than or equal to 1. Now I want to arrive at this particular equation, right? That is, here I can write simply 2 and this would be 4, right? So from this one, sorry, this part is already absorbed actually in the identity. So this will be simply be written as 1 minus, that is 1 minus sine square, that is sine 2x squared. Sorry for the identity. So actually what is happening here, this 2 cos x squared times sine x squared, it merges into this, right? So that is the correct form. Now if you observe here, so what I will do, I will be adding, I can rewrite this expression as, so here we are having 2 minus 2 times sine 2x squared. So this particular expression, this range can be written as that, I can write here 2 minus sine of 2x squared, and this will be less than 2, right? So here I have considered 2 here and I have subtracted this quantity here. So definitely from this, if I reverse the sign, if I write it in the reverse order, so after writing it in the reverse order, we can definitely write this particular inequation. Now from this we can clearly observe that this is nothing but my a squared, right? So from this I can say that a squared is going to belong to this particular range, that is 1 to 2, that's clearly visible. So since a can take the value of integer, so from this I can write that the only possible integer square root for this particular interval, this etc value is positive 1 and negative 1. So here the reason, if I can write it very clearly, that is, it is the possible integer squares in the interval, that is 1 comma 2, 1 to 2 is positive 1 and negative 1. So from this we can clearly observe, and why this positive integer, because you can observe here that whatever value of x has to satisfy for this one, so a will pick up the values from integer. So in that interval, in the given interval, only acceptable integers are positive 1 and negative 1, because square root of if I talk about a square equal to 1, so positive 1 and negative 1 is going to satisfy as an integer. But if I talk about a square is equal to 2, so in that case we do not have integer for that case. So finally from this entire discussion we can say that the set S contains the elements negative 1 and positive 1, and hence we can conclude our answer by saying that the number of elements present in set is 2. So for this problem statement the answer is 2, and hence we have solved this particular equation and counted the number of elements present in set S. So this, if you observe the set P, the only use case of this one was so that we can cancel out this cos 2x with this cos 2x. So because of this given set P, we are able to perform this operation. So from this we are getting 2 as the answer after following all the steps.